Welcome to the deep dive. You're here because you need a high-speed, comprehensive shortcut into one of the most powerful toolkits in software development. I'm talking about the C++ standard library algorithms. We've gone through a stack of sources detailing these essential functions, and our mission today is really to cut through the noise and give you the strategic knowledge you can use.
Exactly. We're not just going to list functions. Think of this more as a structural map for high-performance problem solving. These algorithms, the ones you get from the algorithm header, are battle-tested solutions for common tasks. The real insight is this. When you use the standard library, you are leveraging decades of optimization. Your code will just perform.
And that performance is a guarantee, right? It saves you not just implementation time, but maybe more importantly, those critical debugging cycles. Why handwrite some complex routine when a world-class team has already tuned it for pretty much every platform imaginable?
You wouldn't. This library is the bedrock for almost all modern high-efficiency C++ software.
Okay, so let's unpack this, the foundational layer. These are the workhorses that, almost everyone uses for basic sequence operations.
Right. And let's start with the big one, std.sort. Yes, it orders elements.
Yeah,
But the crucial takeaway isn't what it does, it's how.
how it does it. Okay.
The standard mandates a near-optimal performance. Usually it's an algorithm called intrasort, which is a hybrid. This gives you a guaranteed time complexity of O(n) log n. That's the insight. You get world-class performance every time you call it.
So it's not just a sort, it's a strategically chosen, highly efficient sort.
Okay.
What about moving data? We have std.copy.
Yeah, instead of writing manual loops,
Mhm.
std.copy it moves elements efficiently.
Mm-hmm.
And the beauty of it is how it works with iterators, which is really the cornerstone of the whole standard template library.
Mm-hmm.
It completely abstracts away the container type. So you could be copying from a vector to a list, array to a vector, it doesn't matter.
Yeah.
And it often provides strong exception safety, which is huge.
For data manipulation, two functions really stand out to me. First, std.transform. I see this as like the functional mapping tool of C++ view.
That's a great way to put it. You apply a specific operation to an entire range, and the result goes into another range. It really shifts your thinking from iteration to functional application.
And for totaling things up.
For that, you look in the numeric header for std.accumulate. It's the fundamental building block for reducing a sequence to just a single value. Usually for a sum, but it's more versatile than that.
Right, you can apply any binary operation.
Any binary operation, yeah. Like finding a product or even calculating a hash.
So a question that I think comes up for a lot of people, if sorting is so efficient at O(n) log n, why do we even have a simple linear search like std.find? Why not just sort everything first?
That's an excellent point, and it sets up our next section perfectly. The trade-off is time versus space, really.
Yeah.
std.find is O(n), linear time. It works great on unsorted data if you only need to do one search.
Ah, so it's about the upfront cost.
Exactly. If you have to sort the data first, you're paying that O(n) log n cost just to enable a faster search later.
Yeah.
If you're only searching once, std.find is the pragmatic, cheap choice.
Got it. Okay, so let's talk about the big payoff. When you can guarantee your data is sorted, you unlock a completely new level of efficiency. Let's talk about the binary search operations.
Right. These functions are the whole reason high-performance systems often take that upfront cost of sorting. Binary search cuts the search space in half with every comparison. It's just incredibly fast.
For log n.
So the entry point is std.binary search. Right. That one's pretty simple. It's just a Boolean check, right?
Yeah.
Does this value exist? Yes or no?
Yes or no. Great for a quick lookup when you don't care about the location. But if you need to know where the element is, that's when you move to precision tools like std.lowerBound.
Lower bound. Okay,
Yeah.
so that gives you an iterator to the first element that is not less than the value. It's like finding the absolute starting position for your target. Precisely. So if you have a sequence, say 1, 3, 3, 5, 8, and you search for 3, lower bound points directly to that first 3,
Okay.
and its counterpart is std.upperBound. This one returns an iterator pointing to the first element that is strictly greater than your value.
So in that same example, upper bound would point to the 5. It defines the spot just past the block of 3s.
You got it. That pairing is essential. By finding the start with lower bound and the point just after the end with upper bound, you've perfectly isolated that whole subrange of 3s.
And you did it without having to iterate through them manually.
And for maximum optimization, there's std.equalRange. It does a single, highly optimized binary search and just returns both iterators, the lower and upper bounds, at the same time. It ensures you don't run 2 log n searches when one will do the job.
This is where things get really interesting. We're moving beyond simple lists into functions that handle, high-level math and structural concepts.
Yeah, and as we get into set theory, we have to keep stressing the precondition. These operations require sorted ranges. If your data isn't sorted, you're going to get garbage results.
Right. So the set operations. To merge data, you've got std.setUnion. It computes the union of two sorted ranges, giving you a single range with all the unique elements from both.
And for finding what's common between them, there's std.setIntersection. It returns only the elements present in both ranges. Super useful for data comparison.
And std.setDifference.
That computes the elements present in the first range, but not in the second. And a really great utility check is std.includes. It just checks if one sorted range is completely contained within another.
Okay, that's really useful. Now let's shift gears a bit, away from set theory to heaps. This is a bit more specialized.
It is, but it's so powerful. A heap is a specialized tree-based data structure. And in the C++ standard library, we focus on max heaps, which means the largest element is always right there at the front, ready to go.
And that structure is the foundation for priority queues, right? Where you need to quickly get the element with the highest priority.
Exactly. And the standard gives you the full life cycle. You start with std.makeHeap, which can turn any old range into a valid heap in linear time, on.
And once it's a heap, adding a new element is std.pushHeap.
Yep, and it readjusts the structure in O-log-n, time to maintain the heap property. Very efficient.
And to get that highest priority element out.
That's std.poffheap. It moves the largest element to the end of the range and then reheaps the rest. Again, O-log-n.
So it's always fast to access the max element.
Always. And then you have std.sortHeap, which efficiently turns the heap into a fully sorted sequence. It's basically heap sort. And, of course, std.isheap just to check if your data structure is valid.
Brilliant. Okay, let's talk about one more advanced area, permutations. These functions deal with the actual ordering and arrangement of elements.
And they save just an immense amount of manual effort, especially in combinatorial problems. If you have a sequence, maybe a list of tasks, and you want to try every possible order, you use std.next permutation.
It generates the next arrangement in lexicographical order. For our listeners, what exactly does lexicographical order mean here?
Think of it like dictionary order. If you start with 1, 2, 3, the next permutation is 1, 3, 2, then 2, 1, 3, and so on. std.next permutation just gives you a super optimized way to cycle through every single unique ordering.
And you can go backwards with std.prev permutation.
You can. And finally, a great utility for checking data integrity is std.isPermutation. It tells you if two ranges have the exact same elements, just maybe in a different order.
So if sequence A is just a shuffled version of sequence B?
Exactly that.
Okay, before we get to the real-world applications, let's just touch on conditional operations again. We mentioned std.transform earlier, but its versatility with modern C++ features like lambdas is just central.
It is. And right alongside it, you have std.remove for data hygiene. This function lets you remove elements based on some condition, remove all the zeros or objects that are too old. It replaces these complicated, error-prone manual loops where you can mess up your iterators.
So we've covered a ton of powerful functions. Now for the payoff. What does this all mean for you, the programmer, when you're facing a really complex problem?
It means everything. These are the foundation of efficiency. Our source material pointed to competitive programming problems where milliseconds matter. Take the problem called CD. It's about matching massive lists of unique IDs.
Okay, so like finding the shared items between two big lists, list A and list B.
Exactly. The naive brute force way is to take every item in list A and check it against every item in list B. That's two nested loops. You're looking at a complexity of O and M.
Or ON if they're roughly the same size. And if N and M are, say, 100,000, which isn't even that big, ON is 10 billion operations.
It's a non-starter, a guaranteed runtime failure. The difference between that failure and success is using the standard library. The efficient solution has two steps. First, you sort both lists. That's your ON log n cost.
And second,
you use std.setIntersection. Because the lists are sorted, this function can just do a single, efficient linear pass to find the common elements.
Wow. So you replace 10 billion operations with two sorts and one ON pass. The operation count drops from billions to maybe a few million. That shift, that's modern high-performance coding.
It is. The library encourages you to stop thinking in terms of manual loops and start seeing a structured data problem. You think, I need the intersection of two sets, not, I need to write a double loop.
You're moving the complexity into these proven structural library calls.
And that's the key takeaway here. The C++ standard library algorithms aren't just utilities. They are a conceptual language. They push us to think about data in terms of sequences and sets and heaps, and to use preconditions like sorting to unlock massive speed gains.
It's the difference between trying to mix paint by hand versus just ordering a specific color from a supplier who has it all figured out. You trust their process and you move on to the bigger picture.
And just consider the effort saved on something like std.next permutation. Imagine trying to code the logic to generate the next lexicographical arrangement of, I don't know, a 15-item sequence. Now compare that to a single guaranteed function call. Why does leveraging abstraction define modern high-performance coding? Because performance is no longer about just writing fast code. It's about strategically deploying the fastest code that's already been written.
And that structural thinking, that's what separates the amateur from the expert. An amazing deep dive.
Until next time.